Hi guys, we are back to um, this channel, and you're welcome back to the channel as well. And today we are going to prove certain things, like certain theorems or propositions under the Lebesgue measure or the Lebesgue outer measure. So first of all, there are certain basic things I want us to know, and with the first proof, let's go proofs. Let's get with this proofs. So we are always saying that the outer measure of the empty set is 0. Okay, so you remember I told you that the fact that the outer measure is 0 doesn't mean that it is not measurable. It has a value which is 0. Like the outer measure has a value which is 0, so it's actually measurable, but then its outer measure is 0. And we are going to go through the proofs when we are doing measurability, like when we are talking about measurable sets. Okay, so now let's take the first one. We know that with any set you have the empty sets as a subset of that set. Okay, when I pick let S be an open set. Okay, then I can say that phi, or the empty set, belongs to the open set S, because the empty set is a subset of every set. Okay, yes. So now, since we want to prove that the outer measure of the empty set is 0, we have to pick any arbitrary set. Then we can use that to conclude on that fact. Okay, so actually I'm going to say phi. I'm going to let S we're going to let this S be equal to the open set -1 to n, 1 out of n, where n ranges from 1, 2, 3 up to infinity. So we actually have a set of natural numbers over here. Then we are saying that the empty set belongs to, what's a subset of this? -1 out of n, 1 out of n. Okay, yeah. So now let's pick the outer measure of S. That's going to be 1 out of n minus the negative of 1 out of n, which is going to be 1 out of n plus 1 out of n, and this gives us 2 divided n. So that's the outer measure of n. All right, yes. And we are saying that n ranges from, it is 1, 2, 3 up to infinity. So it means that getting to some points, n has to have a limit. So I can pick the limit of m star at S to be equal to the limit as n approaches infinity of 2 divided by n. But on the left hand side there is no n, so it's actually going to be the same outer measure of S. So I have outer measure of S being equal to the limit as n approaches infinity of the right hand side, and you know that is going to be equal to 0. Okay, yeah, so that's going to be equal to 0. Now we are saying that phi is contained in S. Okay, and from the second proposition that we are going to prove in it later, this actually makes us understand that if A is contained in B, then the outer measure of A should be less than the outer measure of B. Okay, so it means that the outer measure of phi should be less than or equal to the outer measure of S. Okay, then we are saying that m star S, m star phi is less than or equal to 0. Okay, yes. And you know 0, m star, but let me see, let me do this. So this is what we are saying. But then we know that the outer measure of any set, okay, can never be less than 0. So we expect that outer measure of phi should be greater than or equal to 0 at the same time, because but m star of phi should be greater than 0, because length can never be less than 0 here. So but we are saying that this should be greater than or equal to 0, and at the same time we saw that x cannot exceed this 0 here from here. You see, the outer measure of phi of the empty set could never exceed 0. You are saying it's less than or equal to 0. But this is also telling us that you cannot enter the negatives. It is non-negative. The outer measure of every set is non-negative. So you can then conclude that the outer measure of the empty set is equal to 0, because you have two different things, and the only similarity going on here is the equal sign. M star of phi should be less than 0. It can never be less than 0, but you are expecting that it should be less than or equal to 0 because the outer measure of x was 0. But at the same time, the outer measure of phi should be greater than or equal to 0. Therefore, you can say this is equal to 0. Okay, yeah, so that's the proof. That's the proof of that. So let's go to the second proof. And this one I'm going to use illustrations to get you going. I have to be quick with this one. Alright, so we are saying that if A belongs to or is contained in B, then the outer measure of A should be less than the outer measure of B. So now let's use an illustration. I want to use an illustration to do this. So I have my set, which is AB over here. Then this is my set, my big set B. This is my big set B. I can choose any set A, and you can see that this is actually the set A I'm talking about. Okay, this is set A. You see that A is contained in B. A is contained in B. Okay, A is contained in B. So what I'm going to do, before I want to prove this. Okay, I want to prove this. So what I'm going to do is that, okay, let's take the complement of A in B. The complement of A in B is going to be this point to that point, and from that point to that point, right? Right, yeah, that's it. So we can actually see that my set B, okay, is equal to A union of the complement of A in B. So this is actually the complement of A in B. So we see that this union, the complement of A includes this and that, right? So if I find the union of this together with A, I'm getting my B back. That's it. That's it over here, right? Yes. So it means that my outer measure of B is going to be equal to outer measure of A union B, the complement of A in B. That's what we have here. Then this is what we are saying. This is going to be equal to the outer measure of A, and we know that outer measure is actually length, so we don't have the union of outer measures, but this one is going to tend to addition because I pick the length of this, then I add it to another length, so the union changes to plus B given A. So this is the outer measure of B. Okay, sorry, B. All right, so let's visualize this over here. A is contained in B and A has complements. Okay, so you can actually see that the complement of A wasn't empty over here. Okay, there were elements. Okay, so the maximum value or the maximum set of A could have been, so let me use this one to be, let me say this one is contained in that, could be that A was equal to B. So if A is equal to B, then that is when, this is how it's going to look like. If this is my B, okay, then if A is equal to B, then I have this as my A. which means that the complement of A is going to be empty. There is nothing outside A which is in B. Are we getting it? Yes. So from there, I can easily state that with these illustrations, I can state that this element over here, the outer measure, this is when the complement was non-empty. You see that this one is always going to be, the outer measure of this is going to be greater than 0 because there are elements here and they are all intervals. So when I sum them, it's going to be greater than 0. And the extreme point was when the complement was 0 from the illustration I gave initially. So it means that the complement of A in B is always going to be greater than or equal to 0. It can never be less than 0, okay? Because the maximum, the ideal point or the maximum value of A or the maximum set A will be when A is equal to B, and that's not what we are talking about. Like, that is a subset of what we are talking about. Okay, so the outer measure of B given A, or the outer measure of the complement of A in B, is going to be greater than or equal to 0. Therefore, by the sub-additive rule, I can say that M star B is going to be greater or equal to M star A. Okay, because this one is always going to be 0 or more. So if it is 0, then you have M star B being equal to A. But if it is more than 0, then you have the M star B, which contains all these elements, being greater than or equal to the M star A. We get it? Yeah, so this is the proof of the second one. Now to the last proof. To the last proof. So we are saying that M star of A, when A is countable, is always equal to 0. So when you pick any countable sets, or you pick a set of isolated points, okay, isolated points means like they are discrete, okay, then the outer measure of that kind of set is always equal to 0. So before I start with the proof, let's note that the outer measure of any set C, where C is unit set, is equal to 0. So the outer measure of every unit set is equal to 0. So example, when I have this set 1, the outer measure is 0, because before I can even talk of outer measure, the set has to be continuous and it has to be between two different points, but you have only one point over here, so it is basically 0. So that's what I want to do. So if you are saying that A is countable, if A is countable, then we can say that A is defined as a certain x1, right? x2, x3. It is in one-to-one correspondence with the set of natural numbers, okay? Or that there could be a certain xn, okay? So let's say it is countably finite. It could be countably infinite. It doesn't matter where it's going to end. So if it's countably infinite, then it gets to a certain point n, then it stops. But it can go on and on if it is infinite. All right. Then we know that if I want to find M star of A, that's going to be M star of what is defined over here, x1, x2, up to this xn, moving on just like that. Okay, yes. Now, sorry, we can call A is going to be equal to the x1 union x2 union going up to xn, and it's going to follow that order, union following that order. And it is so clear because when you pick any element, say the points 1, 2. The union of 1 and 2 is going to be equal to 1, 2, just like this. You get it? Yeah. So the set of isolated points is actually the union of each of the elements as sets, like sets, the unit sets you have in the union of them. So that's what we have over here. So it is easily understood. Yeah. So my M star of A actually becomes the M star of the union of all xi's. The union of all xi's. So let's do this visually. It's actually M star of x1, sorry, union x2, and so on and so forth, and so on. So from here, you know that M star, when we're doing our initial proof, when M star meets the union, it is going to be the summation, right? It's going to be sum of what we are talking about here. So it's going to be the sum M star of x1, sorry, plus M star of x2 plus going on just like that. Okay, so which is the sum of all M star of xi. But from here, we realize that this is equal to 0. That is also going to be equal to 0. That's going to be equal to 0. Okay, yes. So you can easily see that it's going to be 0 plus 0 plus 0 plus 0 going. Hence, you have M star of A, where A is countable, to be 0. So these are the basic proofs, or these are the proofs to these three propositions over here. So in our next video, we are going to talk about measurable sets. What condition needs to be satisfied for a set to be measurable. Then we are going to prove them all as well. So see you in the next video. If you really like the content of the video, give it a thumbs up.